Hello everyone. It's a great honor to take part in this international conference and introduce our work. Today my topic is insight into dielectric response of ferroelectric relax from statistical modeling. Here is my outline. I will elaborate our work from the following four aspects. Firstly, I would give a short brief introductions, and the second part I would introduce our method carefully, and the third part I will give you some results which were divided into lead-free relaxers and lead-based relaxers. Finally, I will give you a short conclusion. Now let's begin with the introduction. The ferroelectric is an intersection with dielectric, piezoelectric, or pyroelectric materials. There, it owns all of these good properties. It has been widely used in our daily life. It made a capacitor, ferro ramps, detector, or energy storage. One of these material is called the perovskite structure, and this structure is simple and steady. Due to its rich material, it was widely researched, and its doping effect, there it owns various products and modified performance. Depending on the dielectric properties of ferroelectrics, it can be divided into two materials. One is called kinetical relaxum ferroelectrics, and the other is normal ferroelectricities. From this picture, we can see that the normal ferroelectric BTO owns a crucial temperature, while for relaxers, there is no significant first-order transition. And the secondly, we can see that the dielectric properties it's much different. For PMN, its frequency, its dielectric property much relies on the detective AC current, while for BTO, there is no significant differences. So this dielectric properties is well known for experimental results, but numerical generation of this result is challenge work. One of these work, for instance, under given constant and under given temperature, two processes are employed in the fitting of the susceptibilities. The universal relaxer process and the conventional process for higher and lower frequency. On the other hand, there are also many investigations on how the dielectric response depends on the temperature and given frequencies. The most useful equation for fitting around the dielectric peak is the Square law. Unfortunately, this equation can just apply on one side with different parameters. On the one side of TC, it should be one side of parameters. On the right hand of the TC, it should be another one. As shown in the PMN10 PT, it can see we can't use an equation to fit all the curves. There, we focus on this equation. We want to solve it. The most reliable method is the soft model theory. As we can see, the total energy of all dipoles effective Hamiltonian can be written as this function. For the dipole energy itself, it can be written as this equation, depending on Taylor expansion, and kappa, alpha, gamma as experimental parameters determined from first principle calculation. And I means the cell location. For the normal ferroelectrics, expansion parameters should be the same size for each cell. But for relaxers, it should be different. In our work, we focus on individual depots. Therefore, the change of this view implies that the phenomena modes are less important in our analysis. Then we come to the questions: how to describe the dielectric response of relaxers. Here we give out two fundamental axioms. Number one, based on the dynamics, individual depots can be categorized into two different groups. Depots in potential wells and depots out of potential wells. And each group will have different contributions to the total susceptibilities. And number two, we introduce a potential well of average depth EB by assuming various interactions between depot. And this interaction can be include the short-range interaction or long-range interaction, elastic interaction, and so on. Then we come to the statistical modeling of depots. The depot could be belongs to the Boltzmann particles. And the temperature T, the number of depots with kinetic econ, we know it should follow the Maxwell-Boltzmann's distribution. So the number of the depot can give us this equation. Then the total number of depots with kinetic energy that excites the potential well could be obtained by the numerical integration for this equation. And the right line are the final result. ERFC is a complementary error function. So, depending on the conservation of depots, we know the depots in the potential well could be obtained as n minus n1. So the second step is to treat the two sets of depots separately and assign different susceptibilities to them. The right line function is the centerpiece of our works, and P1 and P2 are normalized. Here we come to our results. For the first part, lead-free relaxers, we appended Lx function for our equation. Lx is a long-given function which is describing the orientational polarization under thermofluctuations. Here, the blue dots are the Monte Carlo simulation results, and the red curve is our fitting line. According to this figure, it shows that the overall fitting is good enough to reproduce the result from Monte Carlo simulation. Now we know now we successfully reproduce this curve. We focus on each component of this equation, and P1 and P2 shows opposite trends. As increasing the temperature, and for the second panel, Langevin is normalized and temperature equals to 0 Kelvin. As the right line is the product of Langevin and P1. It shows that this curve also shows the same similar morphology of the curves. And then this part is fitting parameters we used. Now we move to having examined the statical susceptibilities. We now move to the frequency-dependent dielectric response. We had also tested our equations for different frequencies. In here, we know that under AC current, the system couldn't be in a true equilibrium state. Therefore, we came out the W1 functions, and this function follows the Debye relaxation. And the blue dots are Monte Carlo dynamics results. It shows from this figure shows our fitting are good enough. And here is the fitting parameters for these materials. We also showed that the equation for different materials. These results are experimental results. Okay. Now came to the second part. For lead-based relaxers, we noticed that it's much different for no lead-free relaxers due to the BZT poses PNRs which are separated by ZR-reached regions, and lead-based ferroelectric have lead-driven dipoles across the systems. Here we propose to use the slightly modified, well-known correlation relation proposed by Professor Bock and Ye. It reformed into W2 equation, and we added the W2 equation to our simulations. Here we show the fitting of the relative permittivity of these materials and the different frequency. As the Qi1 and the Qi2, we can see that Qi1 are much larger than Qi2. Here here it indicates that the susceptibilities of simple are much relies on the outwell dipoles, which is much different for lead-free relaxers. Here is a comparison for W1 and W2. For lead-based, for the W2 equation, it forms a peak. Well, for lead-free, for W1 equation, it shows no peak. That is, in this figure, it shows the fitting relative permittivity for experimental results. Now is our conclusions. We propose a new microscopy statical approaches to describe the dielectric properties of the relaxers, and we obtained analytical equation for relaxers. Thanks for your attention.
Again, so We should be out of the building by an hour from now. So if you have if you're leaving later today, you can go visit other things in Washington. Please do. I'd appreciate it if you would help me bus the trash and so forth out there. And some people have recognized the pattern, and maybe some people haven't. But this meeting is every year, a week before the Super Bowl. On the Sunday before the Super Bowl till Wednesday noon, okay? So you can plan on that for next year. We don't know the location yet. So if you have ideas for location, please let me know. If you would like to be a co-organizer next year, let me know. And if you have suggestions for invited speakers for next year, let me know. So, anytime between now and next fall. So I appreciate everybody's participation. Next year will be, I think, the 30th year. So maybe we should, put out a book or something, I don't know. Anyway, so I'm looking for ideas for next year. So thank everyone for your participation. Thank you.